Hey, good morning, everyone. Welcome to the GISS Sea Level Rise seminar. We're very glad to have Dr. Tanghua Li, who is a senior research fellow at the Earth Observatory of Singapore at Nanyang Technological University in Singapore. Dr. Li's research interests include interactions of ice sheets, ocean, and solid Earth, and their lasting impact on the Earth system, with a specific focus on modeling glacial isostatic adjustment processes with 3D models and associated sea level ice sheet evolution, vertical land movement, gravity field change, and gravity field change during the last glacial cycle. His research contributes to a better understanding of Earth's rheological structure and glaciation-deglaciation history, which helps to constrain estimates of future sea level change and contribute to understanding the response of ice sheets to climate change. Dr. Li is also interested in interdisciplinary studies exploring sea level change impact and application. And he's joining us from Singapore today, so we're very glad that he was able to join, even though it's rather late over there. So today he'll be talking about sea level change in Singapore and Southeast Asia. So welcome.
Thanks. Thanks for the introduction, Patrick. Hello, everyone. I will say good evening from Singapore and good morning, you guys at the US and North America. So as Patrick introduced, my talk is about the sea level change in Singapore and the surrounding Southeast Asia. I'm from the Earth Observatory of Singapore, the Nanyang Technological University, Singapore. So today, my talk will be divided into like 6 parts. On the left panel, you can see, first, I will give 2 slides of a brief introduction of our institute, the Earth Observatory of Singapore, and then followed by the sea level processes that control the sea level change. Then next will be past, present, and future sea level change in Singapore and Southeast Asia. Finally, 2 slides of summary. So for our institute, the Earth Observatory of Singapore, originally it was a center of research excellence, and then it shifted to a research center under the Nanyang Technological University. So we mainly conduct the fundamental research on the natural hazards, including earthquakes, volcanic eruptions, tsunamis, and climate change in and around Southeast Asia. So here shows you a map of natural hazards threatening our region. So as you can see, the red indicates the tsunami, the hazards, and the seismic. And also you see all the yellow triangles, as you may realize in Southeast Asia have many active volcanoes. And also have the typhoon or the cyclone hazards. And most importantly, you see all the blue, light blue to dark blue, what indicates the sea level rise hazards, which is the main interest of our sea level group within the years. So first, let's see why sea level is changing and what process can contribute to the sea level change. This is a schematic modified after the IPCC AR5. And you see the sea level is contributed by a variety of global, regional, and local processes. They will vary spatially and locally. So most people may know that thermal expansion due to the global warming can cause the sea level to rise. And also you may have the melting glaciers, ice sheets contribute to the sea level rising, as well as due to the loading and unloading of the large ice sheet, you will have the isostatic rebound of the solid Earth, which we know as the Glacial Isostatic Adjustment, also known as GIA. So next, I will introduce from the spatial scale from global, local, and regional. So globally, as you can imagine, there are mainly 2 contributors. The first is the ice mass balance change. Imagine you have a certain volume of the ice. When they melt, the equivalent ice will change into the water, seawater goes into the ocean, and the sea level will be rising. At the same time, as we know, since the Industrial Revolution, the global temperature is rising, and then due to the thermal expansion, the sea level will be rising. And keep in mind, currently on Earth surface, we have two large ice sheets, mainly the Greenland ice sheet and also the Antarctica ice sheet, which can contribute to have the potential to contribute to ice equivalent sea level rise of over 67 meters. So for regionally, because for the North America and or the Northern Europe, Greenland, and also the Antarctica, they were covered by the large ice sheet back to the last glacial maximum. And then you see after that, the ice melt. And then due to release of the load, the surface beneath will uplift. And at the edge of the ice sheet, where the fall bulge that formed during the glaciation will subside and collapse. Mantle material will flow backward to the center of the previous ice. Due to the high viscosity of the lithosphere and the mantle, this isostatic process will last for thousands of years. It's still ongoing now and will go into the future. At the same time, for the contemporary ice melting, such as the Greenland ice melting, the high mountain glaciers, and the Antarctica ice melting, you have the gravitational attraction between the large ice sheet and the ocean. So you see, when the ice accumulates, the gravitational pull will be stronger. So the water pull towards the ice sheet. However, in the contrary, as you see here, when the ice melts, due to the reduced, the pull between the water and the ice sheet will be weaker. Then actually in the near field, you see the sea level will be falling, which means more water will transfer into the far field area, which the equatorial region. So like for Singapore and Southeast Asia, they will experience much more sea level rise than the global mean. At a smaller scale, spatial scale, like for the regionally, here shows you 3 examples of the processes that contribute to the sea level change. The first is about the land subsidence, which is quite common in the whole Southeast Asia, the big cities, such as back to last century in Tokyo, or even now in Jakarta, Indonesia, Manila in Philippines, also like Ho Chi Minh City in Vietnam, mainly due to the overusage of the groundwater, so which caused the local land subsidence very locally, and the magnitude of the subsidence will vary spatially significantly, and that will accelerate the sea level rise because land is subsiding, so relatively sea level is rising. At the same time, in Southeast Asia, we have the large subduction zone, such as in Sumatra, we have the Sumatra subduction zone, and in Manila Trench. So all this, they will have the co-seismic, post-seismic, and inter-seismic vertical deformation, so that the deformation of the solid Earth will also influence the local sea level change. Lastly, here shows you the monsoon due to like the Enzo or the Indian Ocean dipole. Here shows you the northeasterly wind. We have a higher sea level in the near the Singapore and South China Sea. However, during the oppositely southwesterly wind, you see we have a lower sea level near Singapore. So this can cause like up to tens of centimeters scale of the sea level variability locally. So when we talk about the past sea level changes, how do we know the sea level change in the past? And how can we estimate the elevation of the sea level at a certain time in a certain location? So normally, the understanding of our past sea level are derived from a combination of sea level indicators from the paleoenvironmental proxy indicators, such as the coral reefs and atolls, such as micro atolls. So because previously, if you can find in situ records, and then you can date them, you know the age with uncertainty, and you can survey the elevation, and then you know the relationship between the elevation to the paleotidal, like the mean tidal level, then you can estimate the paleo sea level history. At the same time, during the ice covered area, due to the release of the load, the surface will rebound the solid Earth, and then you see a shoreline, actually with the rise species, which means the higher elevation has an older age, which means the level is falling. Also, the archaeological sites and the geomorphological evidence can tell you the information about the past level. And in the Southeast Asia or tropical region, more commonly used is like the oysters and the mangroves. In the mid-latitude and high latitude, you have also the salt marshes, which can all be used to reconstruct the past sea levels. So for one sea level data, normally based on like for in Singapore, we mainly have two indicators that can tell us information of the past sea level. Such as here, you see in Jurong Lake on the upper left and Palu Ubin in the upper right, we have the mangroves. So through the core of the mangrove sediments, and also we do the modern survey to establish the relationship of the present day, the mangrove to the mean tidal level. And then we can do the analog to the core sample to reconstruct the past sea level changes. At the same time, in a coastal area such as Sentosa Island and Nusa Island on the lower Paleo, we can find the big fossil coral microatoll, which can record the high precision sea level information. So normally for one sea level data, we call the sea level index point. They must comprise 4 key information. The first is the location, you know where it is. The second is altitude, you know the elevation. The third is the age, normally such as the radiocarbon dating, you know the age and the age uncertainty. The last also is the most importantly the relationship between the sample and a modern tidal level. Sometimes we call the indicative meaning. Then on the lower right, as you see here, a box, a square, which indicates you the information about the sea level at a certain time period with the uncertainty and a certain elevation, which means the sea level can be anywhere within this rectangle. If you have a series of these sea level index point, the slips, then can tell you the information of a sea level curve. That's only for the data from a certain point value. Then we need to use the model to the background information about the controlling mechanism, control the sea level change. So which is we call the Glacial Isostatic Adjustment, which mainly describe the interaction of the large acid, the ocean, and the solid earth through time, which is my main study area. So for the GIA model, we mainly have 2 inputs. The first is the earth model, which describes the density, elastic properties, and most importantly, the viscosity. And on the above the earth, we have the ice history model, which describes ice coverage and thickness evolution history through time. So here we use the finite element model, unlike the conventional spectral normal mode method, which only allow the earth model to be very radially, and they always assume it's naturally homogeneous, which means only layered model. However, based on the field geology evidence and the seismic tomography results, will support the Earth should be both naturally and radially variable. So we need a 3D model. That's why we use the finite element model, which can define each element with different the properties to solve the sea level equation. And also we consider the rotational feedback, the ocean and ice load. So we have the outputs of all the GIE influences. Most importantly, the sea level. We can also predict the surface motion, both vertically and also laterally, and the gravity field change, and the Earth's rotation feedback, as well as the GIA stress evolution, which may cause the post-glacial seismicity or the volcanic eruptions. So as compared with all the animations we showed before, the GIA considered all this: the mass change, the isostatic response, and also the so-called the GRD, the gravitational, rotational, and deformational influences, which are normally used to derive the sea level fingerprinting based on the GIA. So here is animation shows you the paleotopography and the bathymetry and sea level change through time based on the GIA model. Here we assume the S6G ice model developed by the Toronto group, University of Toronto group. And as you see, back to the LGM, which is about 26,000 years ago present, the whole Northern Europe and North America were covered by the thick over 3 kilometer ice. And when the ice melt due to the water or the locked water in the ice, they run into the ocean. The global mean sea level will rise about 130 meters. And the adjustment of the land to the loading and unloading of the ice, distribution of the melted water, they will cause spatially variable sea level, which will continue to today. And here we choose 3 sample sets. The sample 1 is beneath the ice-covered center near the Hudson Bay. The sample 2, the site 2, is near the ice margin, near the New Jersey. And the site 3 is in the far-field region, which is far away from all the large ice sheets, like Singapore or anywhere in Southeast Asia. So if you look at the sea level pattern, they show very spatially variable sea level record. Like for the site 1, in the near field, due to the reload, the solid earth will rebound. Although the sea level is rising, the rebound uplift rate much higher than the sea level rising rate. So relatively, the RSL actually is decreasing, like you see here. In the sample set 2, which is near the ice margin in the forebulge area, we call the intermediate field. Due to the release of the load, the forebulge will subside. The subsidence will accelerate the sea level rise. So you see a continuous sea level rising. In the far field area, before the mid-Holocene, we see similar as the intermediate field, have the sea level rise, mainly due to the ice equivalent, or we call the eustatic sea level rising. And after the mid-Holocene, you see a sea level falling. So that creates a mid-Holocene highstand. During the mid-Holocene, about 4,000 to 7,000 years before present, you have a higher than present sea level record. So this I will introduce more in the later slides. So with the GIS model output, we can see if we zoom in for only in the Southeast Asia area, you see how the sea level rise change the paleotopography and the landscape. As you see, when sea level is rising, all the land bridges in Southeast Asia connecting Sumatra, Malay Peninsula, Borneo are flooded. And you see, back to the LGM, you can walk from Singapore all the way to Sumatra, to Borneo, or even to part of the Philippines. However, due to the sea level rise, you see, here shows you the time steps, at a series of time steps. You see, on the figure B is about the land area difference compared with today. So which means if you say from the LGM until today, we lost about 2.3 million square kilometers, which is almost exactly the same size of present day the Sunderland. So we lost over 50% of the land area since LGM due to this level rise. Then we come to the idea. Imagine for the historical people, they previously live in a large area of the Sunderland. When the sea level is rising, then their homeland may be flooded, and then they have to migrate. Then we come to the idea to collaborate with the genetic scientists. They have the genetic data, use the population genetic analysis. They can review the population history, and then we try to link the sea level change and the paleotopography change history with the paleogeographic, the map with the genetic scientists, their results. And our analysis demonstrates the earliest instance of forced human migration driven by sea level rise. So on the upper panel, you see here the different color indicates different area and see how the people they migrate when the sea level is rising. On the lower panel from D, you see here we have the result for the land size for mainland Southeast Asia and island Southeast Asia. And also from the genetic analysis, they review the effective population size. And then if you divide it by the land size, you have the density, population density. And then we see they are highly correlated with the fast sea level rise period, especially during the meltwater pulse 1A and 1B event. Then we came to the idea that the historical population migration in Southeast Asia are forced by the sea level rise. So previously we showed the paleotopography and the landmass change. Here, because we have the record in Singapore, the geological records for the paleo sea level data, only back to like 10,000 in the Holocene time period. However, in the Central Sunderland, we have some data can date back to 20,000. And then we also have the tidal gauge data in Singapore. We try to reconstruct a continuous sea level record for the whole Singapore through the whole last glacial maximum, the glacial transition, and Holocene until today. And then we use the area invariable integrated Gaussian process model and try to reconstruct a continuous sea level record here. Although we have the big temporal gaps, we can still give you some information, an idea about how the sea level was in the past. And then we derive the sea level change rate, which tells you the information about the peak of the meltwater pulse 1A, which is around 14,000, and meltwater pulse 1B, which is about 11,000 years before present. Here you may see the rate is slightly lower than the recorded in the geological records, like here, mainly because here our temporal resolution is only like 250 years. So we can't resolve the very high resolution the data here due to the large temporal gap. Also, especially here, you may see from the mid to late Holocene, where we have a highstand, the sea level was higher than present during the mid-Holocene time period. We lack of the data to constrain the magnitude, how high they can reach, magnitude, and also the timing when they reach the peak. So, which means we need more data from the region of Singapore or nearby Southeast Asia to constrain the special phenomenon we call the mid-Holocene highstand, sea level highstand. Then, here I would like to introduce in detail how the mid-Holocene highstand was formed, mainly due to two processes. The first is called on the left, equatorial ocean settling. And you can see during the LGM, you have the large ice sheet. And when the ice sheet melt, you see where the forebulge or clefts, and even when the ice has been fully removed due to the high viscosity, the forebulge will keep subsiding. And then this will create a void, which will accommodate the water transferred from the far-field area, the equatorial area, and then in the far-field area, like Southeast Asia, the sea level will be falling. However, at the same time, in the far-field area, we have the shallow continental shelf, like Southeast Asia. When you have the shallow continental shelf, when the sea level is rising, here, as you see, the increased load of the ocean will depress the sea floor, and offshore, it will subside. Onshore, it will uplift. And then both the equatorial ocean settling and the continental leveling, the two will contribute to the formation of the mid-Holocene sea level highstand, as you can see for the fourth sample set in the far-field area here. So you have a highstand. Previously, we said in Southeast Asia, we cannot constrain the highstand, the peak, the timing, and the magnitude very well because of the lack of the data. So as a J model expert, I tried the model to help identify the location where they might have the highstand preservation of the geological record. So for the field scientists, they should go to these places to collect the sample to reconstruct the mid-Holocene sea level highstand. Here shows you the model prediction at about 6.5 thousand years before present in Southeast Asia for the highstand. As we see, the highstand exists about nearly everywhere in Southeast Asia, and the boundary is consistent with the boundary of the Sunderland, which is in black dashed line. And they were peaked around near the Malacca Strait over 4.5 meter with the magnitude. And then the center, the peaks were centered around the northern Sumatra, northern Java, southwest Borneo, also in the Gulf of Thailand. And then we test how the magnitude, the highstand magnitude, sensitive to the variation of the input parameters, mainly three input parameters tested here: the mesospheric thickness, upper mantle viscosity, and also the lower mantle viscosity. For the mesospheric thickness change, we may say it's relatively insensitive That's mainly because when you change the elastic mesospheric thickness, although the peak, the center of the deformation, they will maybe thicker will be smaller, but also the thicker mesosphere will cause a wider the range, and then the total volume that can accommodate the water will be somehow similar. That's why it's relatively insensitive. However, for the viscosity of the upper mantle and lower mantle, you may see normally they will increase and then they reach like point, then change gradually. However, for the upper mantle viscosity change, when you decrease to like 10 to 19 per 19 Pascal, there will be low highstand. This is mainly because if you have a very low viscosity in the upper mantle, the relaxation time will be very short, which means when you reach the mid-Holocene time period, you already reach a equilibrium. There's no more deformation from the mid-Holocene until present to accumulate to form the highstand. Then we use the present day, the GAPCO 2022 present day topography map, the grid, to generate a map we call a treasure map to identify the location where they may have the potential to preserve the mid-Holocene sea level highstand record. So we try to identify the location. Previously, they were flooded by the sea level, but now they are exposed above the present sea level, which means the location, they should have the information to record the past sea level highstand. So here you see all the red dots indicate the likely area, which is more than 90% of the probability they should have the highstand record. And you see the purple and the green dots indicates the published data derived from the sedimentary records or the coral and oyster materials or these fixed biological indicators. They say they have the highstand record. And we see they all overlap pretty well with our red dots, which means our map is valid to review the location that they may have the potential to preserve the mid-Holocene highstand record. Also in the Northern Asia here, you may see at 2015, they reconstruct the sea level from early Holocene until today. They didn't show any highstand, so also consistent with our record. However, we also notice in the Mekong River Delta, the Bangkok, or even maybe in the west coast of Sumatra, you may see the red dots, which mean from the model perspective, they say there should have some record. However, from all the past publications working on this area, they don't show much of the highstand. On the contrary, they show the sea level previously was lower than present and increased to today. The model shows it should be decreased today. And then there's a discrepancy. And then we would say the discrepancy is due to the long GIE process, such as the subsidence, the compaction due to the and then cause the subsidence, or the post-depositional lowering, or even tectonic signal. So the discrepancy, the mismatch information can be used to derive a long-term subsidence signal caused by the non-GIE process. So in the last slide, we only validated the location. Here, we also compare the magnitude predicted by the GIE model with a variety of different input parameters. We ran an ensemble of the model, then we can generate the GIE prediction with 2 sigma SNT. Then we have the slips within 2 sigma SNT and also the marine emitting data and terrestrial emitting data. For the marine emitting data, which is upward the triangle, which give you the lower bound with the past sea level, which means the past sea level should be all above. And for the terrestrial, we should give it the upper bound, which means the sea level should be below. And then we see here, all the data match well with our model prediction, except for the set 1, which is from the Bangkok. We suspect with this data was higher than all the rest sea level records and also much higher than the prediction. We assume here data affected by some local unknown reason that are not considered in the model. So next, I will talk more about the present day sea level in Singapore and Southeast Asia. So here shows you the pedagogy record globally, only for the long-term records, which means they are over 40 years time period of the record. You may see the coverage of the long-term tidal gauges are especially variable, highly uneven. Like for Southeast Asia, we don't have much, especially like you say in Borneo, even in Singapore, we don't have. And then if we look at Singapore, although Singapore is a very small area, we do have quite a lot of the tidal gauge records. However, they can only date back to 1970s. Only have like 50 years of the record. If you want to go earlier for high resolution record, we don't. Then we try to find some proxy high resolution proxy reconstructions to extend or overlap with the instrumental measurements. In Southeast Asia or in the tropical region, normally you may be able to find the coral microatols, which can probe the high precision constraint for the past sea level. Here is an animation, shows you how the coral microatol grow and with the sea level change. When you have a low water, and then the exposed area, they may die of the coral microatol, and then you may have a die down, and that die down will give you the information about the sea level of the low water sea level at that time if you dig. And then normally based on the coral microatol, you say if the sea level is stable, you will see a stable surface morphology here. And if sea level is rising, you see like here, you have the die down, and you see the central greens are going outwards. However, if sea level is falling, you see like here, and then the die down will show a different morphology. In the center is higher, and central greens will go outwards, will be lower. So all this, each die down can give you information of the past sea level. And then in Singapore, we use the nearby coral microatols, extend the sea level record, instrumental sea level record back to 1910 in early last century. And then we try to run the spatial temporal model, give you a continuous record of the sea level within one segment, two segment entities. So if you only look at the grid, you see that's for the results only use tidal gauge. If you look at the light blue, which gives you the information, we combine the tidal gauge and also the coral microatols. You see the uncertainty of the reconstructed sea level narrowed down by 50%. And also we review the sea level was almost stable before 1990, between 1915 to 1990, 0 plus minus 1.6 millimeter per year. And after that, after 1990, from 1990 to 2019, the sea level increasing to 1 plus minus 2.1 millimeter per year. Here you may see the sea level, the median value is lower than the global mean. That's mainly because in the far-field area, as I introduced before, we were suffered from the sea level falling since the mid-Holocene highstand. So that will compensate certain portion of the sea level, present-day sea level rising. And also, if you look at the range, due to large uncertainty, you still can reach like a global mean about over 3 millimeter per year. So for the future sea level change, we mainly take the IPCC AR6 projections based on 5 scenarios. But here I mainly introduce only 2, the SSP1 1.9 and SSP5 8.5 scenario, how the sea level in Singapore may change. So if you look at the magnitude for 1.9, it may reach 0.37 by end of this century. However, for the SSP5 8.5, the sea level may rise to 0.78 by the end of the century with a rate over nearly 13 millimeter per year. However, the IPCC, those provide the projection called the low confidence, high impact, which mainly due to the uncertainty of the projection for the Antarctica, due to 2 processes, the marine ice shelf instability shown the schematic on the left, and the marine ice cliff instability on the right, due to the cliff failure of the hydrofracturing. So both contribute to the largely uncertain of the contribution of Antarctica to the future sea level change. This is also validated by the field observation. This is a video or the lead PI, Benjamin Horton, also the director of EOS. They went to Antarctica earlier next year, and they saw all this hydrofracturing, which matches the theory. And then if we consider the low confidence, high impact SSP5 8.5 scenario, we see the sea level in Singapore may reach 0.9 by the end of the century, and the range can almost close to 1.7, over 1.7 meter. So previously we reconstruct this level record for the Singapore back to the LGM, and also we take the IPCC R6 projection in the future. So here we try to see, compare the future projection rate, how likely in the geological past it has been exceeded. Like for SSP1 1.9, which is about 3.4 millimeter per year by the end of the century. And as we compare with the proxy record from the geological records, the past sea level, we see they are virtually certain this has been occurred between 15.25 and 13.5 thousand years per present, and also between 9.5 and 8.25. However, we see during the last 5,000 years, it's unlikely, which means less than 33% of the probability, the rate of the RSL exceeded 3.4 millimeter per year, which means even under the SSP1 1.9, it will be the highest rate in the last 5,000 years. If we go to the SSP5 8.5, which is about 11 millimeter per year by the end of the century, and then you will see in the last 8.25 thousand years, it's extremely unlikely, less than 5% of the probability, the rate of the RSL rise exceeded 11 millimeter per year, which means if we really goes into this scenario, in the last more than 8,000 years, it never happened before. So we don't know what may change the whole picture. Previously, we showed the historical population migration in Southeast Asia were forced by sea level rise. So that's maybe the earliest, the so-called climate refuges, or due to the sea level rise. Nowadays, in Jakarta, the previous capital of Indonesia, they have 40% of Jakarta lies below level already. And some parts are sinking by as much as 30 centimeters per year, mainly due to the groundwater withdrawal and then the local subsidence. Then the Indonesia government, they had made the decision, they will change their capital from Jakarta to the southeast of Borneo, the city called Nusantara. So they will change the capital, the political center from Jakarta to Nusantara. This is the present day case that of the population influenced by the sea level. So for Singapore, as you may know, it's a small island, only have like around 730 square kilometers the landmass, and more than 30% of its land area are less than 5 meters above the present sea level. So they are largely suffered from the sea level rising. On the upper right, you may see a figure shows you a picture, shows you the Singapore was suffered from the compound flooding, which means they have two contributors to sea level rise or water level rising, which is due to they have a high precipitation, and coincidentally they have a high tide area coming. So that you see all the main streets were flooded. And on the lower right, you may see why the sea level rising is so crucial, because the sea level or the mean sea level, mean tidal level only improve your baseline. On top of that, you have the tidal range, you have the coastal erosion, the storm surge, which will cause much more hazards. And Singapore realized the climate change and sea level rise as a big issue, big threat, even back to 2019 earlier. Like our Prime Minister said, the Singapore is especially vulnerable to one grave threat, and that's the rising sea levels. So Singapore has been taking action to tackle the climate change and sea level rise issues, including funding the scientists to do fundamental and engineering solutions. So here we have two main projects led by the Earth Observatory of Singapore, the EOS. The first is they call C2, the Southeast Asia Sea Level Change Program. So we have 5 main components from different perspectives, try to give a systematic solution for Singapore. And this has been around for 3 years, and I also have 2 more years to go. And more recently, just founded early this year, we have a so-called climate transformation program, which is a 7-year project, have 5 components and 3 centers. So all these projects are ongoing, and we are hiring more people. If anyone is interested in the work done by the EOS, may go to the website, you may find more information. Thank you.
Thanks very much, Tanghua. Quite interesting. Do we have any questions? Yes, Roger, question.
Nice talk, Tanghua. Can you hear me okay?
Yeah, Roger.
Okay, amazing. Yeah, really nice talk. Great work. And I think probably all of us in the room are jealous of your graphics. Beautiful. My question is about the viscosity sensitivities that you all have done. I wondered if you had explored in 3D GIA space whether Singapore and Southeast Asia or Sunderland is more sensitive to near field viscosities, like closer to the peripheral bulges, or whether it's, or what the sensitivity is like in locally, like what's more important?
That's a very good question. Because for the highstand feature, it also have 2 components, the forebulge flaps and also the continental liverny. For my test, I do for 1D, I do globally. So I haven't go into like fix the near field and only tune the far field, like the nearby region in Southeast Asia, or fix Southeast Asia, tune that. So now I guess the question still is uncertain for me. The next step will be try to do that. Now it's just for 1D. I assume it's homogeneous. For the 3D, I test a few because for in Southeast Asia, we have the subduction zone. So the geometry of the low viscosity area, we lack of the evidence from the seismic anomaly information. So we do have the conics, they are working on the seismologies. They are trying to reconstruct, have a model for the whole region. So I can take that as a constraint for the 3D viscosity structure. But for the global seismic topographic model, resolution here or the is relatively low. So they cannot resolve like for the Sumatra subduction zone or the Manila Trench. So that's a problem. I mean, I would say there's work to do in the future. I need to do. Hope this answers your question.
Yeah, that's great. Thank you.
Thanks.
Are there any other questions? Yes, Klaus.
Yeah, it's about 25 years ago, I was involved in a project in Singapore that had to do with seismic hazards, but at the time, there was a project going on where new islands were built to put petrochemical and other industry on it in Singapore to extend the land. And we were very concerned that they would build it too low. I'm not sure what elevation they actually finally filled it up to, and where they flooded recently during those flooding events in Singapore.
For the land accumulation in Singapore, it is quite important because originally Singapore only had like 500 square kilometers. Now it's more than like 25%. The land area were reclaimed from the shallow ocean. But for the building or the infrastructure, like for Changi Airport, normally they will level up, set the elevation to be like they assume it's like 5 meters above the sea level. So now it's still relatively safe. The mainly like in the coast, like west coastal part, which is connected to the open ocean, when you have the high tide and heavy precipitation, like I showed in the picture, you may have the compound flooding. Then that's the main issue now. They do have some area flooded. True.
Okay.
Any other questions? Okay, well, I guess we can stop there. Thanks again, Tanghua, and
Thanks.
everyone for coming.
Thanks for the invite.